Hello and welcome to the fourth video from the C5 quantitative analysis revision section. This video is on pH curves and titrations. The aim is, after you finish watching this video, you should be able to describe what happens when an acid reacts with an alkali and interpret and draw simple pH titration curves. Right, a neutralisation reaction is essentially the reaction between an acid and an alkali. It forms a salt and water. The reason that it always forms water is because you essentially have H plus ions reacting with OH minus ions. So you've got H, two of them, and an O, which is H2O. The spectator ions, whatever spectator ions are involved, are the ones that come together to form the salt. Basically two ways to measure pH in these situations. In a pH curve you can either use universal indicator, which gives you a full range of colours showing change of pH, or a better way to do it is to use a pH meter, which gives you a numerical digital readout of whatever the pH is when you're carrying out a neutralisation. This gentleman here is carrying out a titration. When carrying out a titration you always use a burette. The burette is graduated and shows how much liquid is delivered into a conical flask. The conical flask usually contains 25 cubic centimetres of the alkali. Alkalis are usually put into the conical flask rather than burette because they can damage glass and they are more dangerous than the acids. You then also add an indicator so you can see the colour change associated with the pH change. Right, here we have two standard pH curves. What you can notice to start with is this is the pH of an acid added to an alkali. To start with, the pH changes very little and you get very rapid change before very slow decrease of pH in the end. This is an acid titration. Starts with a very low pH, which raises slowly before you get a very quick increase around neutral, and a very slow increase following. In both these cases you're starting with 25 cubic centimetres of, in this case, an alkali and an acid, and adding up to 50 cubic centimetres of acid or alkali to each one. In terms of key language you need to be aware of here are these points here, the end point of the reaction. It's when the solution is neutral, i.e. when the pH is 7. In both these situations the pH is 7, the pH is neutral when you've added 25 cubic centimetres of acid or 25 cubic centimetres of alkali to both of the different situations. This isn't always the case, it's just the case on these two graphs. A couple of questions for you to try here. Firstly, the pH of the alkali at the start, that's here, it's 13. What was the pH of the mixture after 30 cubic centimetres of acid had been added? Which is 2. And what volume of acid is needed to exactly neutralise the alkali? Which is 7. Can I apologise for the mistake on this slide? What it should actually say is, what was the pH of the alkali after 10 cubic centimetres of acid had been added? pH there is just over 1, probably say about 1.2. What volume of alkali was needed to reach pH of 11.5? Wish I had a ruler. If you do get a question like this in an exam, please do use a ruler. I'll say around 28 cubic centimetres. What was the total volume of the mixture at the end point? The end point is where it's neutral, so the volume there is 25, added to the volume that you start with of 25 to get the total volume, giving you 50 cubic centimetres. So, in summary on pH curves, neutralisations require precision. Acids can soak up lots of OH ions before they become neutral, and vice versa. Also, pH curves have a very small endpoint where neutralisation has occurred, and you usually add the acid to the alkali and start with 25 cubic centimetres in the conical flask. Moving on to indicators and, more importantly, titration. Right, the hopeful aims of you watching this video. The first thing, you should be able to describe common colour changes of some indicators. You should also be able to explain the need for consistent readings in titration, but that's a given for any experiment. And the most important one, and the hardest one, is to carry out concentration calculations using titration results. So here are some examples of some indicators. This is phenolphthalein. Phenolphthalein is pink in alkaline solutions, and in acidic solutions it goes colourless. It's often used for titrations because it goes from an alkaline pink colour to clear when you get a neutralisation. So it gives a very clear endpoint. This here is litmus. Litmus is red when it's acidic and blue when it's alkaline. Another indicator that you should be aware of is universal indicator. It's not very often used for titrations because it gives a wide range of colour changes. So it's not very precise, but it does give you the approximate pH of a solution. So it is useful in different contexts. So what is a titration? Basically, it's a method used to find out the concentration of an unknown, whether it be an acid or an alkali, using a known concentration of another acid or alkali in a neutralisation reaction. It's carried out in exactly the same way as a pH curve, but you're using a single indicator and you're looking for the volume that gives the end point of the titration. Usually the volume that we neutralise is 25 cubic centimetres. That's added to the conical flask using a pipette and a pipette filler. You add your phenolphthalein to that situation to give the pink colour. And as the acid is added to the alkali, you'll start to notice the pink colour disappear. At the point where the pink colour completely disappears, that is the end point of the reaction. The amount of acid that's used in the neutralisation, the difference between the start and the end readings on the burette, is called the titre. That's the volume of acid that's used and needed to neutralise the alkali. As with any experiment, when you carry out a titration, you want to do things more than once. The reason for that is because repeating experiments gives you consistent results. It allows you to identify anomalies, and it makes you, it enables you to check that you've done the experiment correctly and to calculate a mean titre, which is often more accurate, more precise. Right, in order to carry this out, there are a few things you need to know. The first thing is you need the triangle that you use to work out volume and concentration from the number of moles. The second thing you need to do is to convert all the volumes into DM3. So you've got 0.025 and 0.024. Then you have a three-step calculation. Step 1. How many moles of hydrochloric acid have you got? Well, the volume of hydrochloric acid is 0.024. Multiply the volume of acid by its concentration, 1, gives you the number of moles, 0.024 moles. Step 2 is to assume that in this case, if you have 1 mole of HCl, then you have 1 mole of sodium hydroxide. So if you have 0.024 moles of HCl, then you have 0.024 moles of sodium hydroxide. That's because in this reaction here, it is a 1-to-1 ratio. Finally, step 3. If you divide the number of moles of sodium hydroxide, 0.024, by the volume of sodium hydroxide, 0.025, using the triangle here in the calculation, mole divided by vol gives you concentration, then you should end up with a concentration of 0.98 mol per dm3. It's really important you remember those 3 steps. Often you'll get 4 marks for this. 1 for converting to dm3, 1 for working out the number of moles in the known solution, Another one for knowing the number of moles of hydrochloric acid or whatever acid you're using is the same as the number of moles of sodium hydroxide or whatever alkali you're using. And then the final mark for calculating the end concentration. So you can pick up marks for doing each individual step. Right, we're going to have a go at another calculation here. The first thing to do is to work out the titre in run 4, which is 20.0. Then you need to identify any anomalies. Say this result there is an anomaly, and then you need to work out an average titre. So 19.8, add 20.2, add 20.0, divide that by 3, worst 3 ever, gives you an average of 20.0 cm3. Right, on this slide I've already carried out the first step and I've converted all volumes into DM3. Step 2 is to identify the calculation that you're going to use, the number of moles over the volume times the concentration. Step 1, known solution. We have 0.2 mole per DM3 of hydrochloric acid multiplied volume by concentration multiplied by 0.02. That gives us number of moles of hydrochloric acid. In this case we have 0.004 moles of acid. Step 2, our assumption again that we have a 1:1 ratio. So if we've got 0.004 HCl, we've got 0.004 sodium hydroxide. And step 3, divide those number of moles by the volume of sodium hydroxide used, which is 0.025. This gives us a concentration of sodium hydroxide of 0.16 mol per DM3. So in summary, whenever you get a calculation on this in exams, you will be given an anomaly. Make sure you discount it. The reason for that is probably some sort of error in the experiment. Don't forget the equation that you're using, the number of moles divided by the volume times by the concentration. And to work out the concentration of an unknown liquid, firstly, step 1, multiply the volume times by the concentration to find the number of moles. Step 2, the number of moles is usually equal in the acid and the alkali. And step 3, divide the number of moles present by the average titre. Mole divided by volume gives you the unknown concentration. Make sure that you've converted every volume to DM3 in advance, because there will often be a mark for that. That concludes this video on pH curves and titrations in the unit C5 quantitative analysis. My name is Mr. Clee. If you have any questions about this video or any others in the series, please see me or any of your science teachers. Thanks for watching.